Hi everyone. From this point on, we're going to be talking about data structures for most of the rest of the semester, and trees all day today, including a special kind of tree called a binary heap. So I'm going to start by talking about trees in general. How do we define a tree? A tree is a set of nodes and edges that connect them. And they're connected in a special way. They're connected in such a way that for any two nodes, there is exactly one path connecting those two nodes. Never less than one path, never more than one path. What do I mean by a path? Well, a path has a mathematical definition. It is a sequence of nodes, and that sequence of nodes has to have the property that every consecutive pair of nodes in the sequence is connected by an edge. So there's a picture of a tree. Trees in their most general form don't necessarily point in any direction. But there's a kind of tree you've probably seen plenty of times before called a rooted tree that does establish an ordering on these vertices. So in a rooted tree, we take a tree and we pick one node in that tree, one distinguished node that we call the root. And so in this tree, any one of those nodes could serve as the root. There's nothing about a node that makes it ineligible to be a root, but you have to pick one, and once you pick one, that establishes some properties of the graph. So let's say I take this node here, the black one, and call that the root. When you pick one node to be the root, then you've established a sort of directionality on all of the other nodes that kind of goes in towards the root. Every node has one path that gets you from that node to the root. And once you see what those paths are, you use them to define parents and children in this graph. So every node, let's call node C, with one exception, the root, has a parent. One and only one parent per node, unless you're the root and you don't have a parent at all. And the parent is defined to be the first node that you travel past if you walk on the path from C to the root. So, for example, if I pick this node here, near the upper left, and call it C, there's one path that will get me to the root. You walk this way. And the first node after C that I traverse is C's parent P. And the next node on the path would be P's parent, and so forth. And If P is the parent of C, then of course C is the child of P. Again, one more time, the root has no parent. But every other node does. On the other hand, there's no limit to how many children a node can have. So before I can talk about anything really interesting about trees, I have to give you a whole bunch of definitions. So there's a whole language of trees that we need to learn, and then we can start talking about what you can do with trees. So let's get started on the language of trees. Lots of definitions. A leaf is a node with no children. And an internal node is the opposite of that. It's a node that's not a leaf, or in other words, it's a node that has one or more children. Two nodes are siblings if they have the same parent. We will often talk about the ancestors of a node, call it D. And the ancestors are all the nodes on the path from D to the root. And that includes, well, it includes D's parent and D's parent's parent and D's parent's parent's parent and so on, and the root. But it also includes D itself. So I know it might seem strange to call D one of its own ancestors, but it's one of those mathematical things where the way that you use the word ancestors, it tends to make sense. Usually you want to include a node when you're talking about its ancestors. So the reciprocal of the ancestor relationship is the descendant relationship. So if A is an ancestor of D, then D is a descendant of A. We will often talk about the length of a path through a tree, and the length is the number of edges in the path. And we'll use that to define the depth of a node in a tree. The depth of a node is the length of the path from the root to that node. So one thing I want you to try to remember is depths are numbered from 0. So in other words, the depth of a root is 0. So in other words, when we're counting the depth in a tree, you start counting from 0. The root has depth 0. You have to move away from the root before you get to a depth of 1. So if you think of a game search tree, for instance, the board at the very top, the one you're evaluating now, that's depth 0, not depth 1. Please try to remember that, because there's always people who forget that. And there's a reciprocal relationship to that called the height of a node in a tree. And the height of a node is the length of the longest path from that node to its deepest descendant. So in other words, how far down the tree do you have to go to reach the very lowest you can go going down from that node? And so when you talk about the height of a node, once again, a node that's a leaf node, essentially kind of at the bottom of a tree, at least locally at the bottom of a tree, has height 0. So again, please try to remember that. Heights start at 0. They don't start at 1. If you're a leaf node, your height is 0. We can talk about the height of a whole tree. If you take a whole tree and ask what its height is, that's the same as the height of the root. We will often talk about the subtrees of a tree. So if you think of a tree as being branches, then if you cut off a branch, the piece you cut off is a subtree. And we usually talk about a subtree being rooted at a particular node. So if you pick a node n in the tree, then its subtree is going to be the subset of that tree that consists of that node n and all its descendants. And finally, we will often talk about a special kind of tree called a binary tree. So binary tree has two properties besides being a tree. One is that every node has at most 2 children. If you're a node, you either have 0, 1, or 2 children. The second thing is that every child is either a left child or a right child of its parent, even if the parent only has 1 child. You still have to decide whether you're going to be a left child or a right child. So a very common use of trees is to illustrate the directory structure and the file structure on your hard disk or in one of your directories. So for instance, if you look at the CS61B web pages, they have a certain structure where at the top is the main web page, and that has subdirectories that store your homework and files that store things like the main class web page. And those directories have subdirectories. And so in this structure, this is how you usually draw a rooted tree. You put the root at the top, and you have the children going down the page, of course. And so the node at the top is generally the root node. The leaf nodes are here at the bottom, but they're not all on the same level. Most of them are at a depth of 2, but there's some at a depth, there's that one at a depth of 1 in this example. Index.html is a leaf at depth 1. And the height of this whole tree is 2, because the height of the root node is 2. So that gets us through all the terminology. Are there questions about this? Yes? Are edges the same as nodes? Pardon me? Well, so in this graph here, the labels like lab 1 are nodes, and the edges are these lines that connect the nodes together. So not the same. Other questions? So the next question is, how do you write a data structure, say in Java, that allows you to represent one of these trees? There are several options. I want to start off with the easy, obvious one, and then go to a slightly less obvious one and spend a little more time on that. So the easiest and obvious one, you can find it in Goodrich and Thomasia if you want to read more about it. But what they do is they have a data structure where each node of the tree is represented by a node object in Java. And each node object stores 3 reference. There's one to the item that's stored in that node, the file name or whatever. Every node knows its parent. And every node has a reference to its children. And this is the tricky part, of course, because a node can have any number of children. So how do you store an arbitrary number of children? The obvious way to do that is use a list. And you can use your favorite list data structure to do that. Directories, like the file directories that are on your disk of your computer, actually are usually stored in a format like this. But the data structure that represents the list is quite different than your Java lists because of the way it's laid out very specifically on your disk. You'll learn about that if you take a databases class. But this is the obvious option, and I think you can all see how it works. So I'm going to move on to option number 2. Option number 2 is a more compact version of this. So the basic ideas are still the same, but instead of using a separate list class, what we're going to do is we're going to develop a tree node class that does all the list linking for us internally. So we only need one kind of node. We don't need list nodes and tree nodes. We just need tree nodes. And so option 2 is a tree data structure in which all the sibling tree nodes are directly linked. So they basically have next pointers that allow you to link siblings together all in one structure, all in the same data tree node structure. So I'm going to call this kind of tree a sibtree, and the reason they call it a sibtree is because the siblings are a key part of the representation. And the nodes I will call sibtree nodes. So I'm going to write a little class for the nodes first. Each node can store an item. And its parent. And I'm going to have each sibtree node store 2 other pointers to other sibtree nodes. And those 2 pointers are going to be what allows us to have a singly linked list implicitly included as part of the tree node's data structure. And so each tree node is going to have a reference to its first child, or the leftmost child. But only one. You have a reference to one of your children, but not the others. If you want to find your other children, you need to go to your first child and then walk through the sibling pointers. Every tree node has a pointer to its next sibling. So these next sibling pointers are just like the next pointers in a singly linked list. They're used to link a group of siblings together. And now that we've got our tree nodes, we can build a tree on top of that. So it looks a lot like a list. Instead of storing the head of the list, we're storing the root of the tree. We also store the size, which is the number of items that we're storing in the tree. So this is our data structure for a rooted tree. And let's see what it looks like with that directory file structure that I showed you before. So at the very top, I'm going to have a sibtree object. That stores the root and the size of the tree. Now I don't want to draw little boxes like this and set aside every single sibtree node. So what I'm going to do is I'm going to create a schematic here where I'm going to draw each sibtree node like this, as a rectangle divided into 4 smaller rectangles. And the idea is that in each node I'll store the parent at the top, the item in the middle, the first child at lower left, and the next sibling at lower right. And this will make it a lot easier to draw the tree. So the root node is the top of my file directory structure. You remember it's ~JRS 61B. And the root node, remember, is the only node that has no parent. So we're going to put a null pointer in the parent box. It also has no sibling. The root never has a sibling, so we'll put a null pointer in the next sibling box. But it does have children. So let's draw those children. So there are the 4 children. They all have the same parent, the root node. So I'm going to draw parent pointers from all of them pointing back up at the root. And they are linked together with the next sibling pointers. So homework is going to have a pointer to its next sibling, index.html, which has a pointer to its next sibling lab, which has a pointer to its next sibling lec. So that's where we use the next sibling pointers to build a singly linked list of all the children of the root node. And then this last one, its next sibling pointer is null, because there are no more siblings at that point. And these have children too, or some of them do. Pardon me? If you're trying to find something, it depends what your mechanism for knowing what you're looking for is. So it's kind of an ill-defined question. If you want to search the entire tree, there's a way to do it in linear time, which I'll show you shortly. We'll also be talking later in the semester, probably next week, about binary search trees, which sometimes let you find things faster. It really depends, though, on what you mean by finding something. There's more than one way to define that. So here's homework 1 and here's homework 2. The children of that leftmost child. And so they're linked together in a linked list, just like their parent. They both point up to their parent. And they have no children of their own, so their first child pointers are null. Index.html also has no children of its own, so its first child pointer is going to be null. And then lab has some children. And lec has some children. Anyway, you get the idea, so I'll leave the rest of them out. But this basically is what the sibling tree data structure looks like for those directories we saw before. Yes? Say that louder, please. Can a node have more than one parent? Never. So nothing ever has more than one parent. Other questions? Yes. Can a parent have as many siblings as it wants? Is that the question? A node can have any number of siblings unless it's the root. The root uniquely can have no siblings ever. But every other node could have tons of siblings. Mm-hmm. That homework 2 doesn't know that homework 1 is its left sibling? So, sort of true. The question is, does homework 2 know about homework 1? Well, not directly. Homework 2 does not know about its siblings to the left in any direct way. But if you want to find them, you can. And the way you do that is, if you want to know all the siblings of homework 2, first you go up to the parent. Once you're at the parent, you come back down to the first child, and then you can read off all the siblings of homework 2, including left and right siblings. Mm-hmm. Yeah, you could. If you want to add an extra reference to each node, you can make this a D list instead of just an S list. So now every node would have a next sibling and a previous sibling reference. If you want to do that, you can do that. Would it inviolate any tree invariants? Well, when you design a data structure, you get to decide what the invariants are. If you're going to add prev pointers, that means you need more invariants, just like D lists have more invariants than S lists. But there's no reason you can't do it. You just have to define your invariants correctly for the data structure you want. So now that we've got trees, the next thing I want to talk about is some ways to traverse them. What is a traversal? A traversal is a method for visiting every node in a tree once. And there are different traversals that visit the nodes in different orders. So this may or may not be an answer to your question, sir, about searching through a tree. Now, there are lots of different applications that might want to go through all the nodes in a tree and do different things with it. So we define some general traversals that can be used in many different ways for many different applications. I'll give just a few examples. But typically, you want to either maybe print every node in a tree or perform some calculation on every node in a tree, something like that. We're going to look at 4 different traversals today. 3 of them can be defined recursively. We will start with a pre-order traversal. So the idea of a pre-order traversal is you want to visit each node first, and then visit all of its descendants. Or more specifically, you visit each node before you recursively visit all its children in order from left to right. And we always start at the root. So the root is the very first node visited. And so now I want to give you code to do this, which you should study later. It's not a long code, but it's a little tricky. So you'll notice I'm putting the method preorder in the sibtree node class. We're going to call this on a node, generally the root node, and then it's going to call itself recursively on its children nodes. And they're going to call themselves recursively, or call preorder recursively on their children, and so forth. So preorder, the first thing it always does is visits this node. So this method, visit, is just a generic method that does some sort of calculation. And what kind of calculation it does, again, depends on the application. We'll see different applications will do different things in this visit. After visiting this node, we visit our first child, if we have one. Well, to be more precise, we call pre-order recursively on our first child, which is going to have the effect of visiting all of the descendants of this node. After we visited all our children, we need to do our part in making sure that all of our parents' children get visited by calling pre-order recursively on the next sibling. So as I said before, this code is a little bit tricky, even though it's short. I strongly recommend that you practice it. And by practice it, I mean sometime after class or when you have free time, take a piece of paper, take this code, take the directory tree that I showed you before, and simulate the computer and try to draw what the computer would do as it runs this code. Draw the stack, draw the tree, draw the variables, see how the recursive structure of this pre-order method calls itself. And if you do it right, then for a tree like this, it will visit the nodes in this order. So we call pre-order on the root node, and pre-order always visits this node first. So the root node is always the first node visited in pre-order. Then you call pre-order recursively on its first child, and that means we visit the first child. The child calls pre-order recursively on its first child. So the left child's left child gets visited third. Now this node doesn't have any children to call pre-order on, so we're done with its children, and so it goes on to call pre-order on its next sibling. And so its sibling gets visited fourth, and that one calls pre-order on its next sibling, which gets visited fifth. And now there are no more children or siblings to visit in this part of the tree, so the recursion backtracks all the way to the root. And it backtracks to node 2. It backtracks to node 2. And then node 2 calls pre-order on its next sibling. So this node gets visited. That one calls pre-order on its first child. And that one calls pre-order on its next sibling. At this point, we have visited every node, and the recursion will backtrack all the way to the top, and we're done. Any questions about this? Yeah. Well, when you're doing recursion, you always have to backtrack through any node where the recursion doesn't end. So I wouldn't really call that a disadvantage. And it's not, the code does have to go through that node twice, once on the way down and once when the recursion is unwinding back up. But it's not correct to say you visit that node twice. You only visit the node when you actually call the method visit. So that only happens once. Other questions? All right. One thing that's a little surprising maybe and hard to grok about this is that each node is visited only once, and you call preorder only once. And the running time for preorder, not counting the cost of the recursion of the subcalls, is going to be constant time per node. So each node is visited and gets a preorder call only once. And so if you add up the time for preorder on every recursive call, it's linear time in the number of nodes in the tree. And by the way, not only is the worst case time order n, but the best case time is omega of n as well, because you always do visit every node once, and that's going to take order n time no matter what. Question? What's the maximum? The maximum height of the stack is going to be exactly the same as the maximum height of the tree plus 1 for the root. So this tree has height 2. Your stack is going to never have a height bigger than 3, at least on this call, because you have one stack frame on the stack for each node down the path. I'm sorry, I'm wrong. I'm missing this up with binary tree traversal. With a preorder tree traversal, it basically depends on how many siblings you have for one parent. So, because of course things are linked like this. So the maximum number of stack frames in this example would be, when you go down this path, you're going to have these 5 frames on the stack. So for that particular tree, that's the worst case. There were other questions over here? Over there. Why do 4 and 5 get called before 6? Well, from node 2, what's happening? Node 2 is calling preorder on its child first, and later it's calling preorder on its sibling. So 2 calls preorder on its first child 3 first. Later it's going to call preorder on its sibling 6. But when we call preorder on 3, 3 gets busy and takes care of its siblings recursively before that recursion has a chance to unwind so that 2 can call preorder on its sibling. Yes? Oh, you do. So after you visit node 5, the recursion unwinds. You pop a stack frame and you go back to node 4. You pop a stack frame and you go back to node 3. It's just that as you do that, there's nothing else to do at node 4 or node 3. They've already done everything they can. And so yes, it will unwind from 5 to 4 to 3 to 2, and then 2 can call preorder on 6. Other questions? So one natural thing you can do with the pre-order traversal is have each visit call, the visit method call, print the name of the current node. And if you do that, that's a natural way to list a directory structure. So a pre-order traversal of that directory I showed you at the beginning of the lecture would look like this. You start by printing the root, you print its first child, you print the children of the first child, you would go back and you print the second child of the root, so this is what you naturally get when you do a pre-order traversal of a directory with subdirectories. You get a nice readable printout that shows you the structure of that tree. Our second traversal is called a post-order traversal. And in a post-order traversal, when you call post-order on a node, you visit all its descendants first, and then you visit the node itself last. So it's similar to pre-order. It's just we're putting off visiting myself until I visited all of my children. And so if you come back to this pre-order code I wrote before, to change that into post-order code, there's essentially one change you have to make, which is you take this dot visit and you move it down here. There's one other change you usually make too, which is you rename it from pre-order to post-order, because now it's doing post-order. But the functional change is just that one line. This dot visit moves down so that you visit your first child, and that will visit all the other descendants before you visit yourself. So let's come back to that tree that I showed you down here. Let's do that tree again. All right, so remember this was pre-order. Now we're going to do post-order. So with post-order, just like with pre-order, we generally start at the root. So we call post-order on the root, but we don't actually visit the root yet. We call post-order recursively on its first child, which calls post-order recursively on its first child. And then, since that one has no child of its own, now it can visit itself. So the node that gets visited first is actually this one, at the far lower left. Then, after it visits itself, it visits its next sibling. So this one gets visited, and then this one gets visited. And now this node has no children and no next sibling, so the recursion starts to unwind. Pop off the stack frame, pop off a stack frame, pop off a stack frame, and we're back to the child of the root, which can now visit itself because its children have all been visited. Now that we've done that, we go and visit its next sibling. We call post order on its next sibling. We don't visit it yet, because it's going to visit its first child first. And so we come down to this child, and that one has no child of its own, so we can visit it now. And then we go and look at its next sibling and recursively visit that. And this one has no children, no siblings, so we come back and unwind the recursion, pop a stack frame, pop another stack frame, and now we can visit the right child of the root. Then we unwind the recursion back to 4, back to the root, and now we can finally visit the root last. And post order always visits the root last. So that's a post order traversal. Any questions about that? Yeah. I'm sorry, I can't hear you at all. Can you talk a lot louder, please? What is the advantage of post order over pre-order? Post order has different applications than pre-order. So I showed you an example before where you can use pre-order to print the structure of your directory. If you do that with post order, it's not very reasonable, but what post order would be good for is, suppose I want to sum the total disk space used by all of the files in that root directory, including all of the subdirectories. Well, in order to find out the total disk space in all of this tree, I need to start at the roots, count up the amount of space each file at the bottom takes, and then sub those files up, sum that disk space up for the subdirectories, and then sum those up for the top level directory. So, to say that again, post order is a natural way to sum the total disk space. And the reason why it's the natural way, again, is because if you have a tree like this, you have to start by counting the files in this subdirectory, adding up their disk space. Then you need to sum up the files in this subdirectory, add up their disk space. Only after you've done that can you go up and sum up the total disk space used here and by its descendants. And only when you've done this for all of the children of the root can you finally go up to the root and sum the total disk space for the entire tree. So by the way, the post-order code is trickier than it looks. So the advice I gave you on pretending that you're the computer and actually executing the pre-order code for practice, that advice goes double for post-order. So there's a third kind of traversal that is specific to binary trees. It's called an in-order traversal. And here the idea is that you recursively traverse the left subtree of the node, and by the left subtree, I mean the subtree that's rooted at the left child. And then visit the root itself. Then visit the root's right subtree. And so, for instance, if I have an expression tree that looks like this, the idea is that I'm going to start my traversal at the root, as always, but I'm not going to visit the plus yet. I'm going to visit its left subtree first. So I go down to here. I'm not going to visit that one yet. I'm going to visit its left subtree first. So I go down to that one. It has no children, and so I now visit the 3. Then I unwind the recursion back to the star. I can visit that star now. And then I visit its right child. The 7 has no children, so I can visit it now. Then I unwind the recursion back to the root, and now I can visit the root. Then I do the same thing with the right subtree. When you have an expression tree and you visit it in order, then you wind up with an expression which is called an infix expression. One of the funny things about infix expressions is that when you write them out as expressions, it's not always obvious what the order of operations should be. Should this be done first? Or is that wrong? Should this be done first? Well, this particular tree actually means this, but the infix expression doesn't tell you that. If you visit the same expression tree in pre-order, you get a different kind of expression called a prefix expression. And the prefix expression, unlike the infix expression, is unambiguous. There's no ambiguity about which order you're supposed to do the operations in. But humans aren't used to reading this. But if you ask your grandparents, they might be able to tell you about the days when digital calculators forced you to type your expressions in postfix, which is what you get when you do a post-order traversal of an expression tree, which is also an unambiguous expression of that mathematical expression. Any questions about that? Mm-hmm. So you don't modify the previous code to do in order because binary trees usually have a different data structure than the one I showed you. And I'll show you that data structure in next Monday's class, I think. So I'll leave that aside for now, but come back to it. Question there. Sorry, can you speak a little louder, please? Something about... All I heard was the words numerical values. I'll come over there. Oh. Okay, the question is, for a tree like this, would the numerical values be only in the leaves? And the answer is yes, they would be. So with this kind of expression tree, the internal nodes are always operators, and the leaves are always numbers, basically. So there is a fourth kind of traversal called a level order traversal. In a level order traversal is different than the other traversals that we've seen in that you really can't define it recursively. So you visit the root, then you visit all the depth 1 nodes from left to right. Then all the depth 2 nodes. And then all the depth 3 nodes and all the depth 4 nodes and so forth. So if you take this tree we were just looking at and you do its level order traversal, then that would be plus times exponent 3742, which is not meaningful for this particular tree, but that's what a level order traversal is. And in a few minutes we'll see something where a level order traversal is actually useful. Now, again, unlike the three previous traversals, this is not easy to write recursive code for. I mean, it's physically possible, but it's just not a natural or easy way to do it. So what we do instead is we do level order traversals with the following algorithm that uses a queue. So the idea is we're going to maintain a queue which initially contains the root and nothing else. And then you're going to repeat the following steps as many times as necessary. Dequeue a node from the queue, visit it, and enqueue all its children. In order, of course, from left to right. And you just repeat these three steps until the queue is empty. And I invite you to try that out when you go home on the tree I just drew to see how that works. One thought on this is that if you take this algorithm and you change it in the following way, use a stack instead of a queue, and when you put the children on, push them on in reverse order, from right to left instead of from left to right. If you make those two changes, then you get a pre-order traversal. It would be instructive, again, when you go home to think about why that's true. Any questions about that? Our next topic is priority queues, which are another important data structure that's based on a tree and actually is a good application of level order traversals as well. So a priority queue is kind of like a dictionary in some ways. It contains a bunch of entries. Each entry consists of a key and a value that's associated with that key. However, whereas a dictionary is used to look up arbitrary keys, a priority queue is used to prioritize different events or different values. And so the keys usually have a total ordering. The keys might be numbers, or if they are, say, strings, then they would have an ordering like alphabetical order. So we define a total order on the keys. Now, the main thing that priority queues allow you to do is add entries at any time and identify the key with the smallest priority, or the priority that comes first in this total ordering. And that's the only key that you can easily find, but that limitation is what makes priority queues fast. So here are the main operations you can do on priority queues. You've got an insert operation, which adds an entry to the priority queue, sort of like a hash table does. you have a min operation that returns the entry with the minimum key. And you have a remove min operation, which also returns the entry with the minimum key, but also removes it from the priority queue. A priority queue can have other operations besides these, but these are the ones we want to make go fast. Other operations might be a lot slower. So to illustrate these operations, you can think of a priority queue as sort of a box that has a bunch of things in it. And each of them has a priority, which is the number attached to that thing. And so if I want, I can insert a new entry with a new key like 5 and some additional information, a database record or whatever, that I will call the value. And so that essentially just throws that new thing into the priority queue. But these things are arranged internally in a special way that makes it possible to find the minimum one fast. So if I do remove min, it modifies the priority queue to remove the item with the minimum key. And it also returns that item, so you can look at it. Or if you want, you can look at the minimum item without actually removing it. But the tricky part of this is the fact that whenever you remove the minimum key, you have to figure out really fast what the new minimum key is so you're ready to return that fast. So why do we want these operations? Well, probably the number one thing that priority queues are used for is what's called event queues for event simulations. So you might imagine that you want to simulate a fire in the building and the fire department's response to that fire. One way to do that is to build a simulation where you add events to the event queue, like at time 0, the first floor starts burning. And then you can have rules for adding new events to the queue, such as when the fire gets this big, somebody calls the fire department. 3 minutes after the fire department is called, the first fire truck shows up. 12 minutes after the first floor starts burning, the second floor starts burning, and so forth. And so the priority queue will be used to put events on the queue with an associated time. The time is the priority. And in order to do the simulation, you have an event loop that repeatedly looks at the queue, takes the event with the earliest time off of the queue, because that's the one that's going to happen next, and simulates that event. And when you simulate an event, it might add new events to the queue. So once the second floor starts burning, you have a rule that 13 minutes later, the third floor will start burning. So you add that event to your event queue. And just keep looping through taking an event off the queue, processing it. That may add new events to the queue. Then you take the next event off the queue. So you're simulating through time. So are there any questions about what priority queues are? Mm-hmm. There can be multiple values with the same key. Because if you think of an event simulation, for instance, there might be two different events that happen at exactly the same time. In fact, all the events could have the same key. It's possible. Mm-hmm. Do the keys have to be numbers? No, you could use strings and put them in alphabetical order. You can use anything you want as a key as long as you can have an ordering on it. Or in other words, write a compare to method. So anything that implements the comparable interface, you can do this. All right, so what I've given you so far is an abstract data type. It's just like a dictionary is an abstract data type. Now I want to talk about a particular implementation of that abstract data type, just like a hash table is one of many ways to implement a dictionary. Question in the back? How do you find the new event after you remove the previous min? That's what the whole rest of this lecture is about. How to do that fast. So, to answer that question, I'm going to talk about a data structure called a binary heap, which is one way to implement a priority queue. This is definitely not the only way to implement a priority queue, but it is a particularly fast one, and it gives you a sense of data structures and the kind of thinking that can go on to make fast algorithms for doing operations like this. So a binary heap stores all the items or all the entries as a complete binary tree. A complete binary tree is a binary tree in which every row is full, except possibly the bottom row. And if the bottom row is not full, well, at least it's filled in from left to right. So here's an example of a complete binary tree. So, the root at depth 0, that's a full row. Its children at depth 1, that's a full row. Its grandchildren at depth 2, that's a full row. Its great-grandchildren at depth 3, that's not a full row, but we always fill it in from the far left and move to the right as we have to. And by the way, this 8 here, that's an example of a left child. So this is a binary tree. Every child is either a left child or a right child. And in a complete binary tree, you can't have a right child without having a left child. Now, we're going to store our priority queues as complete binary trees that have an additional property, which is that they are binary heaps. A binary heap is a complete binary tree with one additional property. Its entries satisfy something called the heap order property. So what is the heap order property? No child has a key less than its parents. Your key is always greater than or equal to your parent's key. And you'll notice that I've drawn this heap here to have the heap order property. So for instance, the root is 2, and its children are both bigger than 2. And the children of 5 are both bigger than 5. They could be equal, but they can't be smaller. One really interesting property of binary trees that we're going to use to make sure that our algorithms are correct is the fact that every subtree of a binary heap is a binary heap. So for instance, if you look at the subtree rooted at 5, that's a binary heap too, because any subtree of a complete binary tree is a complete binary tree, and it still satisfies the heap order property. Now, there are several different ways that you could store a binary heap. You could store it just as a standard tree if you wanted, but we're going to do something a little trickier. When you have a complete binary tree, it allows you to use a special space-saving array format that makes the data structure run faster. You don't have to use this, but it's a great option that works really fast in practice. So we want to store a complete binary tree just as a simple array. And so we are going to map the tree nodes to array indices with something called a level numbering. And what a level numbering does is it does a level order traversal of the tree. With the root at index 1. So let's come back to this heap I drew. Here is how we store that heap as an array. So level numbering means I'm going to take the root and put it at index 1. So there's the root. I'm going to take its 2 children next and write them in order from left to right. I'm going to take the grandchildren next, 9, 6, 11, 4. And then I go down to the next level, depth 3, and write those in, 17, 10, 8 from left to right. And so when you have a complete binary tree, you can just store it as an array like this, and it makes things really simple. You don't need all the tree nodes and the parent pointers and the child pointers and the sibling pointers. That all goes away. One of the super clever things about this level numbering, I should mention, we have deliberately left index 0 empty because it makes the numbering work out better. It makes the indices work out better in the following way. If you have a node at index I, and you want to know what its children are, well, the children of the node at index I are stored at indices 2i and 2i plus 1. So there's just a really simple way, given a node's index, to figure out where its children are stored. and its parent too. Because the parent's index is I over 2. And if I is odd, you round down. So it's the floor of I over 2. So what's cool about this is that no node needs to store explicit references that point to its children or point to its parent. You just do a little math and you know where the parents and the children are. And that's much cheaper and faster for the computer to do. So you could use a tree-based data structure, or you could use this array data structure, and it runs maybe 2 or 3 times as fast in practice. So we need to store in each node 2 things, the key and the value. So one way to do it is to have an array of tree nodes. Where each tree node stores a key and a value. Another way to do this, by the way, is you could use 2 separate arrays. You can have an array of references to the keys and an array of references to the values. So, are there any questions about this, how we represent a binary heap? Mm-hmm. Pretty much all you have is the array. So the question is, all you have is the array, no other tree? And the answer is yes, though you do have one other thing. You need to keep a separate field that tells you how many items are in the tree. So you have that array, and you have the length of the number of items. Those 2 things are all you need. So now that we know how to store these things, I want to talk about how we implement the 3 main operations really quickly. Let's start with the min operation. This one's easy. The heap order property means that the smallest key is always at the root. So you return the entry at the root. And if the heap is empty, if there are no items in the heap at all, then you just return null or throw an exception, depending which interface you prefer. So let's go on to something more challenging. Let's look at the insert operation. So we want to insert an entry with a key k and a value v. And Goodrich and Thomasia defined the prototype for this so it returns an entry, which is just an object that points to the key and the value that you gave it, I guess for consistency with the other 2 operations. So I'm going to call the entry x. X will be my way of representing an entry that includes both the key and the value. What we're going to do is we're going to place this new entry at the very bottom level of the tree in the in the leftmost empty spot. And if the bottom level of the tree is full, you start a new level and you place the new item at the far left. Now, in the array-based implementation, if you're representing your tree in level numbering, then That's the first tree location in the array, not counting the index 0, which we never use. Okay, so we found a space to put the new entry, but it probably violates the heap order property. It is probably not bigger than its parent. It might be, but usually it's not. So we need to fix that. And so the next step is we're going to correct the heap order property by having the entry bubble up through the heap until it reaches its natural level. Okay, what do I mean by that? I'll be more precise now. I mean the following by bubbling up. We basically have a loop that says while x's key is less than its parent's key, the heap order property is not satisfied, so we swap x with its parent. And if you do that swap, then you repeat that again with x's new parent. So eventually one of two things will happen. Either the key will rise to a point where its parent is now smaller or equally small, and it'll stop, or it'll rise all the way up to the root and stop there. So to make this clear, here's an example of this algorithm in motion. So there's the heap I had before. Now I'm going to insert 2. And that means I look for the first empty place in the heap and I put a 2 there. And now the heap order property is not satisfied because 2 is less than 6. So that's no good. So I swap 2 with its parent. And now I test again. The 2 has risen from the bottom of the tree up 1 level. I compare it with its parent again. 2 is less than 5, so we're still not happy. We swap 2 with its parent. And we check again. So now the 2 has risen up to the depth 1. Now it is equal to its parent, which is good enough. So we're not going to swap again. We can stop here. We're done. And if you look, you can see that the heap order property is satisfied everywhere in this heap. Question? This process is definitely not constant time. So this process actually is log n time, because if there are n items in the tree, then the depth of the tree is log n. So this is big O of log n time. Other questions? It is possible to do a version of this where the nodes do have more than 2 children. That is possible. The only thing is that if the nodes have a really large number of children, then the remove operation is not going to be fast. Other questions? Mm-hmm. So I do not recommend switching the nodes because that's just way more complexity than necessary. So I would just swap the entries inside the nodes and leave the nodes alone. All right, now let's look at how do you remove an item fast. The problem with removing an item is that it's easy to remove the item. It's at the root of the tree. The hard part is restoring the heap order property. You have to, when you remove the item from the root, you have to find some other item to fill the hole in the root. And that's the tricky part. So first thing is, when you run remove min, the heap might be empty. If there are no items, just return null or throw an exception. But if there's at least one item, then here's what we do. You begin by removing the item at the root, well, the whole entry at the root, and save it for the return value. We can't return it yet because we have to fix the heap first. So now we have a big hole at the root of the tree. We need to fill it. And we fill it the cheap way by just taking the last entry in the tree and moving it to the root. And let's call that entry X. We're going to need a name for it. So now we have a complete binary tree again. We've moved the last node to the root. The shape of the tree is good. The heap order property is almost certainly not good because we've just taken a node that's probably really big and moved it to the root where we're supposed to have the entries that are smallest. So we need to fix that, and we fix that by bubbling X down the heap. And what that means is if X has a child whose key is smaller, then we swap X with one of its 2 children. Which child? Whichever one has the smallest key. So to put it another way, while X is greater than one or both of its children, then you swap X with whichever child is smallest. And then you keep repeating this until X is less than or equal to all its children, or X reaches a leaf node and can't go down any further. So let's go back to our original tree. And see what happens when you do remove min. So we're going to take the 2 out of the tree completely. It's gone. And to fix it up, we need to move something in to fill that space, so we take the very last node, the 8. Oops. So the reason why we took the 8 is because we want the tree to have the correct shape, and that means we need to remove this node. So we might as well take the 8 and put it at the top. and then fix up the heap order property. So 8 is right now bigger than both its children, so heap order property is not good at all. So we swap it with one of its two children, namely the smaller one, which is the 3. And at this point now the 8 is smaller than one of its children, so we feel like we're making progress, but it's still bigger than one of its children, so we're going to swap again with the smaller child. And at this point we are happy. Now, in this case, the child made it all the way down to a leaf node. That doesn't always happen. Here's another example, just so you see this a few times. So here's an example where the 4 starts to bubble down the tree, but does not go all the way down to a leaf node, because it reaches a point where it's happy it's smaller than both of its children. Was there a question back there? Question here. You need the assumption that the tree is complete, mainly so that we can have this nice compact way of storing it in an array. If you don't have a complete tree, well, the other thing that's difficult is you want to make sure the tree never gets taller than necessary. You don't want the tree to be taller than big O of log n. So having a complete tree means you always know where to go to remove a node when you do a remove min. It's more about efficiency, yeah. You could have a tree of any shape at all. As long as it satisfies the heap order property, you could make it work. It just might be slow because it might be deeper than necessary. Other questions? So I've given you these 3 operations. Let me summarize the running times. And what I want to do here is I actually want to consider not just the binary heap, but 2 other data structures you might use that are just really simple ways to implement a priority queue. So a priority queue does not have to be this super fancy data structure with this super fancy algorithm. You could just use a sorted list or a sorted array to store all of the entries, and then since it's sorted, it's easy to find one with a minimum key. The only difficult part is when you're inserting something new, you have to find the right place to put it in the sorted list. Or you could use an unsorted list, which allows you to insert things really fast, but then you have to spend a while looking for them when you do remove min. So, with these 3 different data structures for implementing a priority queue, how much does the min operation cost? Well, in a binary heap, it's super fast. You just look at the root. In a sorted list, it's also super fast because the list is sorted. You just look at the end of the list or the beginning, depending how you've sorted it. If you have an unsorted list, then you actually have to search through the whole list to find the minimum item. So that's really expensive. Then there's the insert operation. And just for completeness, I'll look at both the worst case and the best case time, since they're a little different. So when you're doing insert on a binary heap, that takes theta log n time. And I will say more about why that's true in a minute, but the running time is proportional to the height of the heap, which is log n. When you are doing insert on a sorted list or a sorted array, you actually have to find the right place to insert the thing that you're inserting. Then you have to move, if it's an array, you have to move a bunch of items over to make room for it. So that's going to be slow. That takes theta n time. If you have an unsorted list, inserting something is really fast. You just add it to the end. And the best case time, well, with a binary heap, when you insert something, sometimes you get lucky and you don't have to bubble it at all. So it could take constant time. And with a sorted list, sometimes oh yeah. Sometimes you get lucky and you find the right place to insert the thing really quickly. And of course, with an unsorted list, the best case time can't be any slower than the worst case time. Finally, there are the remove min operations. Again, I'll do the worst case and the best case time. So with a binary heap, again, remove min, you bubble something down the heap. The worst case time is the height of the heap. So that's theta of log n. And the best case time of theta 1 happens if every key in the heap is equal. For a sorted list, remove min is really fast because the list is sorted, so you know where the min is. Though if you're using a sorted array, keep it sorted from largest to smallest so that the smallest is at the end. That makes it easier to remove or add. For an unsorted list, remove min is really slow because you have to search through the whole list for the min. So there's 3 different data structures for doing the same thing, for doing priority queues. And some of them are better at some operations and some of them are better at others, you know. If you want a fast remove min, go for a sorted list. If you want a fast insert, go for an unsorted list. But almost all applications, they're going to do about an equal amount of insert and remove. So what you really want is something where insert plus remove is the fastest. And so insert plus remove for a binary heap is order log n. That's fast. For the other 2 data structures, it's order n, which is much, much slower. So that's why we like binary heaps. A few things about why does insert and remove min take log n time? Well, at each level of the tree, it takes order 1 time to compare x with its parent and swap. So that's all you have to do per level. So now the running time is constant time per level of the tree in the worst case. And it so happens that it's not hard to show that an n-node complete binary tree has a height of the floor of the base 2 logarithm of n. And so that's why it takes theta of log n worst case time. So this, by the way, is the exact height. This isn't a big O. This is the exact number. And for remove min, the same explanation. You're spending constant time per level of the tree for log n levels. Any questions about that? Uh-huh. Why is the best case for an unsorted list, that one. So there is really no way to be certain that you have the minimum unless you look at every single item in the list, because something else might be smaller if you haven't looked at it. In the blue shirt? Well, or I'm sorry, is it constant time? So you're talking about insert with a sorted array, this one here? Okay. With an array. Yes. So if you have an array and you want to insert something, it is true that you can do binary search and you can find the right place to insert it in log n time. But then, yes, you do have to push all the other stuff over to make room for the new thing. So you wind up taking a bunch of array items and copying them one place over. And that's going to take order n time in the worst case. And there's no way to avoid doing that. Other questions? Yeah. Well, this is big O and big omega, because each big theta means it's both big O and big omega. So one thing to remember is that the notations big O and big omega are totally independent of what is the function that we're actually bounding. So the worst case running time for n items is one function. The best case running time for n items is a different function. You can talk about big O or big omega of either of those functions. So there's one more operation you should all know about called bottom-up heap construction. Suppose we are given a bunch of randomly ordered entries and we want to make a heap out of them. You could insert them one by one. That would take n log n time. Turns out there's something faster. There's a way to do it in linear time. And so I think this is listed in the Goodrich and Thomasia textbook as a method called bottom-up heap. And the idea is first you make a complete binary tree out of the entries in any order. So it's not a heap yet. So now I've just got a complete binary tree with numbers in some random order, and I need to enforce the heap order property. How fast can I do that? Well, the algorithm is this. You work backward through all of the internal nodes. Remember, internal nodes are the non-leaf nodes. So you go from the last internal node in the level numbering to the root, and that means reverse order in the array. And when you visit a node this way, you bubble its entry down, just like in remove min. And so I will draw an example of that here, where we start with the last internal node, and we bubble it down. So that means we swap it with its smallest child. And then we take the second last internal node and we bubble it down. Swap it with its smallest child. And then we take the root node last and bubble it down. And now we have a heap. And it turns out that the running time for this is always in linear time. And I'm not going to explain why now, but I will tell you that there is a very beautiful pictorial argument for why this is true, and you can see it on page 371 of Goodrich and Thomasia textbook. And I'll guess I won't see you on Monday because it's spring break next week, right? Yeah. So I hope you all have good luck on the project, get it done quickly, and I'll see you after the break.